Welcome back. We saw last time how starting from an input node, we have the ability to take our rendering and process it, to turn it into a different image. To this image we saw we can apply color balance or apply perspective distortion or however many other transformations that we will see later in the lessons. What we're going to focus on today is the information that can be given to us by the render layer's input node. Let's look at this starting scene that, if you want, you can download in the link that you find in the video description. That Blender already gives us information that is named here on the right side of the node. The first one is image, which is the final rendered image. Then we have alpha, which is a numerical type of information that we can imagine a little bit like a black and white image. Let's try to see together what it is. We hold down the CTRL and Shift keys and click on alpha. We see that Blender has connected the alpha output with the viewer node, and we see this white image. It means that every single pixel in our image has a value of 1. 1 is white, where the opacity is maximum. If it were black, that would meant that the opacity is minimal, that is, the image at that point is transparent. In this case, we see everything white. It means that our image is completely opaque. There are no elements of transparency. We will see then maybe later on some practical examples of alpha channel. Let's continue. We have the noisy image, that is the image to which denoise has not been applied. In fact, we see that you can see the grain very well, while in the original image this grain disappears. Finally, we have light group 1 and light group 2. These two light groups, I created them within the scene, and we will see later how to create these light groups. However, let's say that we have the possibility to see individually the effects that do precisely these light sources that are grouped into light group 1 and light group 2. Let's go and see. This is the first one, while this is the second one. So we see that Blender does not give us as input the simple image rendered, but gives us a set of information quite distinct from each other that we can go and combine together to either go and adjust each parameter individually or to go and create particular effects. For example, we could use this group of lights too to go and create a kind of glow to add as an outline to these three objects. What Blender allows us to have, however, is a much more nuanced set of information. Let's go look together within the properties, the view layer properties section. We see that we have the ability to select within the passage group, that is passages, a considerable amount of information. Let's try to enable all of them, and we see that contextually in the input node the respective entries appear. So as we go to add them, all this information is made available to us. We don't necessarily need all of them, though. In the interest of dealing with compositing in depth, we are going to go through them one by one. We see at the bottom that we have two lists. The first is the AOV shader, and the second is the light groups. As already mentioned, the light groups are the light groups. The AOV shaders are values that we can go and get from each individual material that we have created in the scene. We can then insert output type nodes within the materials to go and get information from the materials themselves. We will see this later. Instead, let's go back to our render layer node, which has become significantly more imposing than before, and let's go and see what all this data is that's being made available to us. In order to do that, however, we have to relaunch the rendering because in fact Blender has not yet calculated them. So we press F12 again to relaunch it. So let's go back to compositing, and now we can go and analyze point by point these new layers that are given to us by Blender. Alpha we've already seen. Depth is the depth of field. In this case, the impression is that we see a white image, but in reality we see that there are slightly darker areas. To see them better, we are going to insert a node that allows us to perform mathematical operations. With Shift A, we call up the add converter math command. This node allows us to go and vary the input numbers. So we go to insert it on the link that goes from depth to the viewer node, and we go to select multiply as the type of operation. By multiplying the input numbers by 0.5, we are going to divide them. Let's try to put an even smaller number, for example 0.1, and we see very well now the depth values of this image that at first seemed completely white. These values arise in order to be able to give us the ability to go and apply depth of field to our image. However, no one prohibits us from using them to make any other kind of evaluation. The limitation lies only in our imagination. No one also prohibits us from exporting this single image to be used within any other photo retouching software. Let's go ahead in our exploration, and with Ctrl Shift, let's go and click on Mist. Mist is a kind of fog effect that allows you to apply more depth to the image. It is always a much more appreciable mathematical value than depth, which would be the distance of the objects from the focal point of our camera. And if we want to make a comparison, you should imagine seeing mountains in the background of a photograph. These mountains, the further away they are, the clearer they appear. Here this is kind of the same effect. We see how the object closer to the camera turns out darker, while objects further away are precisely lighter. Position, normal, vector, and UV are four types of information that are vector in nature, that is, they are not real images, although we will see that in fact they are, but they are information about individual vectors. Let's go look at the first position. Look at how this is in fact an image, but has colors with an actually strange distribution. If you remember, in the basic course we talked about the textures that are used precisely in the normal parameter that have this purplish color between blue and purple. Well, the concept is this: these types of maps are used to show us how the single ray of light is deflected for each pixel in our image, and the direction is given on the X, Y, and Z axis. There are three axes and a color is applied to each of them. For the Z axis the color blue, for the X axis the color red, and for the Y axis the color green. What does this mean? It means that in this area where we see blue, the vectors have a direction mostly parallel to the Z axis, that is towards our eye, as if this vector is coming out of the monitor straight towards us. In contrast, here at the bottom we have areas colored red. Here the vector indicates the direction along the x-axis, while in the areas colored green, the direction of movement is along the y-axis. All other areas, the purple, blue, and yellow ones, are positions where the vectors are neither parallel to the x-axis nor parallel to the y-axis or z-axis. Depending on their slope, the RGB values will be mixed. Precisely these value triads will be used to give direction to the vectors. Thus we see that position, normal, vector, and UV have three completely different colorations. Vector in this case is all black, but they all have this principle. Blue for those vectors parallel to the z-axis, red for vectors parallel to the x-axis, and green for those vectors parallel to the y-axis. All the colors. In between are vectors that are not parallel to any of the three axes, but are skewed by certain values. In particular, the position value tells us the position of different objects within the scene. The normal value tells us the slants of the surface, normals used for shading. Vector, on the other hand, is used for the calculation of motion blur. Since there are no moving objects, it has no reason to exist in this specific case. UV, on the other hand, is used to represent where the meshes have been mapped. Since the mapping is two-dimensional, the value with the blue component, that is, the one representing the vectors parallel to the z-axis, actually have no reason to exist, however, since we are always talking about triads of values, they cannot not be included. Then we have index object. This is used to create a mask that allows us to physically separate each object by its index number. This is always a numeric value that is represented to us here as a black and white image, just as happens with the alpha channel, depth, and mist value. Let us try to use the multiply node to see with greater detail these differences. Here you see now, we can more easily understand how these three objects that seem to be colored the same way actually have three different shades of gray. This will allow us in the compositing phase to separate the three objects and go and take only that single object, for example, to apply a mask to it. In a completely similar way, we have the material index. We always have a mask. We always have three objects with three colors slightly different from each other. These are three gray scales that allow us to have the material index. So material 1, material 2, and material 3, and we can go and select each individual material and then extrapolate it from the scene. Well, for this lesson, we'll stop here. I'll remind you that if you'd like to stay up to date on video releases, you can subscribe to the channel. In the description of this video, you will find the index to the individual contents of this lesson and the ability to go download the scene used to make these examples, and you will have the ability to eventually access the handouts. As always, I thank you for following me, and I will see you again soon.